Hello everyone, this is Viraj. Today I am going to discuss on comparative analysis of QNA L4 GENODE, a study of micro-based operating systems. These are the contents that I am going to discuss now. Starting with introduction. A microkernel is a type of kernel that plays a crucial role in managing system resources. What makes it different from other kernel architecture is its implementation of user services and kernel services in separate address space. By dividing these services into distinct address space, a microkernel ensures that failure in user services do not impact the kernel services. This separation provides a significant advantage in terms of system stability. One of the fundamental aspects of microkernel is its reliance on message passing for communication between application and server in the user address space. While this method might be slower in execution, it guarantees the integrity of operating system. The microkernel primarily handles essential operations such as IPC, memory management, and CPU scheduling. Other functionalities such as device driver, applications IPC, and file servers are moved out of kernel mode and run into user mode. This design choice results in a small kernel space which can even fit in the L1 cache. Furthermore, adding a new server becomes much easier as it can be integrated into the user service address space without requiring modification to the kernel space. Q4 is an real-time operating system developed by BlackBerry Limited. QNX is renowned for its exceptional reliability and scalability. It has become a preferred choice for embedded system applications that require strict time guarantee. Its ability to handle critical tasks with utmost precision makes it high suitable for mission critical application. Next, let's explore L4 microkernel, often referred as 4th generation microkernel. L4 microkernel follows a minimalistic design, offering only essential abstractions such as threading scheduling, IPC, and virtual memory management. This approach allows L4 kernel to achieve small size, high performance, and strong isolation between components. The L4 microkernel family has gained significant recognition for its efficiency and ability to power resource-constrained devices. Next, moving to GENODE, a framework specially designed for building microkernel-based operating systems. GENODE adopts a component-based approach where various system components such as device type, file systems, and network stacks are isolated from each other. These components communicate via well-defined infrastructure, enabling flexibility and modularity in system design. GNode provides a solid foundation for constructing security and reliability systems with its emphasis on isolation and clear interference. Let's take a brief journey into the history of microkernel approach. The concept of microkernel approach to operating system has been around for more than 3 decades. One of the earliest microkernel based operating system was Chorus, which emerged in earlier 1980s. Chorus was specially designed for embedded systems and distributed computer applications, showcasing the earlier potential of the microkernel architecture. QNX is real-time operating system which was designed in earlier 1980s. Quantum Software System developed the initial version of QNX in 1982. It is designed for microkernel-based solution for real-time systems. Over the years, QNX has evolved and gained popularity in various industries. In 2010, it was acquired by Research in Motion, now known as BlackBerry Limited. Moving to L4 microkernel, which has made significant contribution to the field of operating systems. It is emergent in 1990. It originated from the work of Ledeck at the Technical University of Kassel in Germany. Ledeck in inventing L3 Microkernel laid the foundation for subsequent development, resulting in the creation of different L4 microkernel like L4K, Pistachio, and SCL4. These L4 microkernel are renowned for their small size, high performance, and strong isolation between components. Moving forward to GENODE, a framework that gained recognition for building microkernel-based operating systems. GENODE began as a research project at Dresden University of Technology in Germany in mid-2000. It is built on foundation of L4 operating systems and has a noticeable framework for constructing security and resilience system. Let's discuss the goals and purposes. QNX focus on providing a reliable and deterministic real-time operating systems, while L4 and GNode can support real-time applications. Their primary emphasis is not on real-time capabilities. QNX places a strong emphasis on high availability, fault tolerance, and quick recovery from failures. It is not a primary focus of L4 and GNode. QNX is designed to be high scalable. Both L4 and GNode are also scalable, may not have the same breadth of hardware support as QNX. QNX guarantees deterministic performance, while L4 and GNode can provide predictable performance. Deterministic guarantees are not a primary focus. QNX incorporates security features, but both L4 and GNode prioritize security. L4 aims for minimalistic and lightweight microkernel design, while QNX and GNode prioritize modularity. Both QNX and GNode also support portability, but L4 portability focus is more explicit. L4 includes version specifically designed for visualization, while visualization can be achieved with QNX and GNode. It may require additional customization and adaptations. QNX may also be used for research, but both L4 and GNode serves as a platform for research and experimental in operating systems. QNX and L4 can be studied for education purpose. GNode is specially used as an education tool for understanding operating systems design principles. Now let's explore the design and implementation aspects of operating systems. QNX, known for its small footprints, it is designed with modularity, scalability, and real-time capability in mind. Its microkernel implements four key services: inter-processor communication, low-level network communication, process scheduling, and interrupt dispatching. With its small size, QNX achieves excellent performance and can comfortably fit with an on-chip CPU cache of 8K. The core of QNX consists of small microkernel that handles essential functions such as thread scheduling, IPC, and resource management. Additional services and functionality like file systems, networking, and device drives can be added to meet specific requirements. QNX is primarily implemented in C and C++. L4 keeps the kernel minimal and provides only essential services. The core functionality of the L4 microkernel includes inter-process communication, thread scheduling, and memory management. L4 designs principle focus on simplicity, efficiency, and minimalization. The microkernel is implemented in assembly language, and C allows for low-level control and high performance. GNode takes a unique approach as a security operating system architect. It aims to minimize system complexity for each security-sensitive application individually. GNode achieves this by employing a strict organizational structure for all software components and applications. It maintains a tree processor where the parent processor defines the virtual environment for the child process. GNode focuses on protecting name, process identification name, and other critical information to enhance security. The design of GNode revolves around high modularity, versatility, security, and resource management. It promotes the idea of break down complex system into small system independent components called capabilities. Let's talk about memory management strategies employed by operating systems. QNX utilizes virtual memory systems for efficient memory management. It employs a demand-based memory model where memory pages are loaded into physical memory only when they are accessed, which reduces unnecessary memory usage. QNX leverages page tables and hardware support to manage the mapping between virtual address and physical address. To ensure the security, QNX utilizes memory protection key to restrict access to specific memory regions, ensuring the integrity of system. Additionally, QNX supports shared memory, enabling processes to share memory regions for efficient inter-process communication. In contrast, the L4 microkernel takes a minimalistic approach to memory management. It focuses on providing basic mechanisms for memory allocation and protection, allowing user-level servers to implement their own memory management policies. L4 supports memory protection mechanism, enabling user level to control access right to the memory region and enforces isolation between processes. This flexibility allows for customization and adaptability based on specific application requirements. Similarly, Genome follows a similar approach to L4 in terms of memory management. It adopts a high modularity and compound-based architecture, empowering user-level servers to define their own memory management policies. Genode also emphasizes the use of capability-based security, where capability represents access to rights to resources, including memory regions. This capability-based approach enhances security and provides fine-grained control over resources access, further enhancing the overall system security and isolation. Coming to complexity, QNX provides a comprehensive set of features and tools which may introduce some complexity, especially for simple or resource-constrained applications. L4 microkernel architecture promotes simplicity and modularity, but it may require additional development efforts and expertise to integrate external components for more additional functionality. Genome focus more on security and isolation may introduce additional complexity, particularly when configuration and managing compound-based systems. Whereas in cost, QNX is commercial operating systems and required license fee. This can be disadvantageous for small-scale projects or those with budget constraints. L4 depends on variant and specific use cases. L4 can either be open source or commercial license. Open source versions are generally more cost efficient. Genome is an open source framework, which means it's freely available and can be cost efficient choice for projects. QNX is primarily developed and maintained by QNX Software Systems, which was acquired by BlackBerry Limited in 2010. QNX is widely used in automotive, industry, medical, and other embedded systems. Kencoast is a Germany company that specialized in development and supporting of L4-based solutions. They provide consulting services, develop custom L4-based systems, and offer products such as L4RE, microkernel, and related tools. GENODE Lab is the German company that offers commercial services and supports for GENODE OS framework. They provide consulting development and training services related to GENODE technology. Let's discuss advantages and disadvantages. Real-time capability. QNX is known for its strong real-time performance, making it suitable for applications that require precise time and responsiveness. While L4 does not focus specially on real-time capabilities, its microkernel architecture provides efficient inter-process communication and low overhead, contributing to good real-time performance. Geno's based design allows for fine-grained control over time and resource allocation, making it possible to build real-time systems if configured accordingly. Robustness and reliability. QNS is Security. QNX provides robust and security features and has been widely adopted in security critical applications. L4 microkernel design facilitates strong isolation between components, making it inherent more security against certain type of vulnerabilities. GENODE put a strong emphasis on security and isolation with a design that aims to minimize the attack surface. Hardware support. QNX has relatively better hardware support compared to L4 and GENODE. L4 has limited hardware support compared to QNX, especially for niche or specialized hardware. GNOME hardware support may vary depending upon the availability of devices and modularity. Performance on overhead. QNX is known for its reliable capability and efficient performance, offers low latency. L4 microkernel design generally result in efficient performance with low overhead. GNOME emphasis on security and isolation may introduce performance overhead compared to more lightweight operating systems. Let's discuss future trends. Performance. QNX may involve further optimization for better real-time responsiveness and scalability. L4 may focus on improvement performance through enhanced scheduling algorithm, reduced context switching overhead, and efficient inter-process communication mechanism. GNode may include optimization resources management and scheduling policies to improve overall performance and scalability. Security. QNX may involve enhanced security protocols, encryption, and secure boot mechanism to mitigate emergency threats. L4 may include advanced in formal verification techniques and secure hardware integration to further strengthen security. GNode may involve continuous security auditing, improving hardware support for security features, and advancement in visualization techniques. Flexibility and modularity. QNX may involve extending supports for emerging hardware architecture, further modularization of components, and increasing compatibility with open source software. L4 may include improved support for visualization, device drives, frameworks, and tools for easy system configuration and customization. GNode may involve expanding the set of availability components, referring the components inference, and further streamlining the integrated process. Internet of Things. QNX in this space may involve further optimization for low power and resource constrained devices, enhancing connectivity options, and integrating with IoT devices, platform, and protocols. L4 this content may include providing more specialized IoT focused libraries, frameworks, and security enhanced tailored for resource constrained environment. GNode in this domain may involve developing specific components for edge device management, improving integration with IoT protocols and standards, and optimization for low power and distributed computing environment. Open source collaboration. QNX may involve increasing collaboration with third-party software vendors and industry partners to expand the platform capability. L4 may involve increasing community involvement, third-party contribution, and creation of collaborative platform for sharing L4-based projects and research. GNode may involve community growth, encounter third-party component development, and extending collaboration with academic and industry to drive innovation. These are the references that are used for this project. Thank you.